ahead and go to my
in
deal here.
chapter 8, or wait, no, sublimation.
So this is actually the problem right here. And
Oh, wait, no,
yeah, we'd use the sublimation energy, that's chapter 8, 107 kilojoules per mole.
That was part of it. So,
And then ionization energy, which is 3.4, and that's the 496. And then hydration, 3.8. Yeah. And then we'd substitute those in.
is the sublimation energy, is that on a table somewhere? Or is that
Yes. Do you guys have your books to look that up? Sorry. Yeah, or if you send me an email to remind me, I have the digital, so I can actually click on that chapter 8 thing, and it'll take me somewhere nearby.
Okay.
Yeah. I just don't remember exactly where it is in chapter 8. Not surprising, right? Now, note that this is a little bit different here, this E naught here, than the actual value would be, because you're going to be doing a theoretical calculation, right? And a linear theoretical calculation. The fact that it gets pretty close is actually really good, because calculation-wise, as long as you can find the values, of course. This is pretty easy, right? The only hard part of it is finding the values, because they're kind of scattered throughout, right? That is one thing that would have really been nice for this book to have done, is put the tables into an appendix. And that's where you'd actually want to look if you want to find that in chapter 8, is you can look up the sublimation energy, just sublimation energy, and the, not the appendice, but the index at the back. And that'll bring you to sublimation energy every time it's said. Okay? If you have the digital copy, of course, you can just go to chapter 8, Control F,
yeah.
sublimation energy. Though the digital copy has its own set of issues. Let me tell you. Did you know the digital copy stopped letting me copy and paste from it? For like 2 days? Yeah. Yeah, it's back now. So I can copy and paste now and get my figures. I did do like these screenshots of my actual screen. That thing, man. I've never seen a book that doesn't give you the actual figures for you to be able to put in your slides. They usually always give you like zip files of the figures. That's why all my figures look like crap. All right, and I obviously do not have a department to make figures for me. So. I know you're all surprised, aren't you? But anybody's a really good artist, by the way. Make some figures for me. Oh, I got a really funny story for you guys if you want it real quick. I got given a reaction mechanism made by ChatGPT. It was insane. You know how they do like the multiple arms and fingers that pop up and then go away? And well, they do the same thing with carbon skeletons and nitrogens, I'll tell you that. It was wild. I've never actually been given one of those before. Oh, it was bad. That was something. Never seen anything like it. Okay. So we're going to go ahead and go on to the chapter 12 now. All right, and so this is going to be the organometallic chemistry. And you're going to notice that of the first part of this chapter, you're going to not have one single item that would have been in the previous chapters. That's it. Yeah. It's actually surprisingly self-contained as far as the information goes. The most important thing that you had to have picked up from previous is coordination, and you have to have the symmetry, an idea of symmetry, just like you did for the molecular orbital theory, right? And then, of course, the molecular orbital theory that we had done. Okay, And so now we're going to be talking a bit about organometallic chemistry. You all are going to notice, because you've all had organic chemistry, many of you with me, but some of you not, you will notice there is a tremendous amount of overlap. Okay? The big difference being we're focusing on things that have metals involved, right? Okay. Which, ironically enough, for everybody in my organic chemistry, we're actually ended up overlapping here, didn't we? Yeah. Because we just started cupric, alkyl cuprates, and Grignards and lithiums, right? So, kind of amusing. That was not intentional, by the way. I wish I had been intentional, but it's not. So the structure of Zeiss salts, this is actually the original organometallic compound. And what's interesting about this is actually an ethene group, isn't it? We have a double bond carbon here. It has a negative charge. And what's happening here is the platinum actually is bonding to the pi electrons here, not on one of the ends. It's actually bonding to the pi bond. Okay? Because remember that this platinum is going to be very positively charged. It's going to have these very large d orbitals, right, that can expand pretty far away from the platinum. And so we can actually form things like this in organometallic chemistry. Okay? And this is where this sort of starts diverging and becomes kind of interesting, is that we can take things that are lone pairs normally, that are pi bonds normally, and we can bond them with metals. Because the metals have a weak enough electronegativity that they won't actually be able to take the electrons. Okay? And so typically if you did something like this with anything else, right? With any organic compound, you'd be taking these electrons and there'd be a reaction there. Yeah. Not here. Okay? This is a stable-ish compound. Like, I wouldn't expose it to air a lot or moisture. But you can keep this long enough to test in labs. Okay? So right here, this is your first sort of table that you need to understand some information from. So one of the things we have to talk about is many, but I need to stress not all. Okay? This is one of those quote-unquote rules where I'm giving you a rule for the majority of situations, but the rule definitely can be broken, just like rules in society, right? So the organic metallic compounds, they are going to follow the effective atomic number, and this is abbreviated EAN. This is actually the rule by Sidgwick, and this is actually normally known as the 18 electron rule. And if you look at your periodic table at the point where you have transition metals added, which are going to be a lot of these compounds, really the majority of these, because they're going to require d orbitals, you'll notice that we would be an 18 electron valence shell. Okay? And so that's your valence shell, isn't it? Now, this rule is not inviolable, but again, to violate this, you would have to have some very unusual, pretty energetic conditions, right? Okay? Something that would violate that because of extreme stability or extremely high energies. Okay? Okay, so your symbol here, which is this in-looking symbol, this is going to be known as hapticity. So the hapticity of a ligand. Everybody's comfortable with that language ligand, right? Remember your ligands from before? Which part of those are they? If we were looking up here. Which ones are the ligands? You got it. Perfect. Yep. And then this would be your metal that these are attached to, right? Or coordinated to. Okay. Okay. All right. Now, note that we have so far mostly had things that coordinate once to these, right? And only once. This is even how here only coordinates once per, right? That doesn't necessarily have to be that way, does it? You can have things that attach at multiple points, can't you? Whether that's covalent, hydrogen bonding, or in this case, coordinations, right? So we can have things that multiply coordinate. Okay. So this is going to be defined as the number of carbon atoms in a ligand that will be directly bonded to the metal. So for example, cyclopentadienyl ligand, there's three possibilities. There's an N1, where we'll have one of the carbons directly bonded to the metal. There's an N3, which is going to be three of them bonded directly to the metal. And then there's an N5, which is going to be five of those carbons directly bonded to the metal. And so that would be your options for hapticity. Okay. So for the N5 again, all five of the carbon atoms would be equidistant from your metal center. And it would look a bit like the metal is a little crown on top of it. Okay? With all five of them having direct connections. Kind of like you'd take in your hand and grab something in the middle. Okay? And that's actually where this comes from, the naming. Ligand as in claw. Okay? And so it literally is claw attaching to. Okay? So, in that case there, this is going to be, for example, the ferrocene molecule that you'd see this. All 6 pi electrons would be used in that bonding. So for the N1, only your terminal carbon is going to be bonded to the metal. And that's going to be arranged so it's identical to a bound alkyl group, kind of like a methyl off there. Okay. The N3 cyclopentadienyl compounds are going to have 3 of the carbons. They'll be equidistant from the metal. And they're going to donate 4 of the electrons from your 2 double bonds so that it sits off-center over those. Okay? Oh, electron counts. Yeah. So I had to split the chart because you guys couldn't read it. Yeah. And so this is the charges of these compounds, these ligands. This right here is the electron counts involved. So for example, here we have 2 pi bonds, right? 4 electrons total. Okay. Yeah. These are mostly lone pairs here. So like lone pairs, and some of them are a pi bond overlapping. So they're 2 electrons. And then these ones are ones where we're going to have like, for example, this is a benzene. Have you guys ever seen the test that happens for like a phenyl group? No? That's a little disappointing. Okay, so you can actually test for phenyl groups by adding iron, 3+. And what will happen is in a benzene, you'll get a very, very light yellow color. So you're basically not visible. Okay? But if you have a phenyl group, it's going to shift that color so it's visible in the reddish. Okay? So you'll get like a very like purple-ish color. Okay? And so what would happen is if you have a phenyl group here, any type of phenyl attached to anything, like, the OH off there, this is going to give you a purple color because the iron is going to attach right down on top there. Like a little crown. And it'll associate with these 6 electrons in those resonance structure. Okay. And that's the sort of stuff we're looking at. You've kind of seen some of this, but you probably didn't actually understand what was going on. It probably wasn't pointed out before. Okay. All right. So this is what the molecular orbital diagram would look like for one of these. So right here, we're going to have nickel on this side. And over here, we have CO. We have 4 of them. And these are going to be the sp hybrid orbitals for those 4 that are going to be involved in this binding, okay, in this ligand structure. And so what we're going to see here is we typically are going to use our d orbitals, and you're going to use your s orbitals here. Now note that most of this character is going to end up with your d orbitals, isn't it? Okay? And that's because your metals typically have s and d orbitals that are available, right, on that shell. Okay. And so based on this molecular orbital theory diagram here, we can actually make some estimations, as it were. And so what you're going to sort of estimate is your ligand electrons are going to fill the lower lying bonding molecular orbitals. And then the valence electrons on the metals is going to typically occupy the molecular orbitals that will have predominantly your d character. Those would be the ones directly generated by your D. See that? Yeah. And this is going to have to do with the symmetry of these things. To bond, what do we have to have them happen? They have to be in the same area, right? Okay. And so, for example, if we were looking at something that's only in the xy plane and we're trying to bond it with a z p orbital, can't bond together, right? Different planes, different areas, can't overlap. Okay? And so this is partially what's going on here, and why, for example, your ligands, if you look down here, your ligands are close in energy to your bonding orbitals, aren't they? Then up here, your higher energy orbitals that are closer to non-bonding, like this one right here, non-bonding, right? Those ones are mostly generated by your d orbitals. See that? Okay. All right, so let's talk about some general tendencies for an organometallic compound to be either saturated or non-saturated or unsaturated, excuse me. I forgot my water. The organometallics are going to tend to obey the 18 electron rule. So if they tend to obey that 18 electron rule, i.e. they get 18 electrons in them, they're going to be saturated. Those that have less than 18 valence electrons are going to tend to be called unsaturated because they don't have the full orbital filled out, right? Their valence shell is not filled. Is that making sense so far? So if we look down at the D block, those ones would all have 18 electrons that can fill out the valence shell, right? And so saturated fills the entire valence shell, or tends to. Okay? Unsaturated tends to not fill the entire valence shell. And typically you cannot get above 18 electrons, though do note that the F block you could very much get 18. You can get more than 18 electrons at the F block. But we don't do a lot of stuff in the F block because they don't exist for very long. Uh-huh.
The
Radius.
Oh, radius. Okay.
Yep. Yeah.
Which is unsaturated.
Yeah. So chi again, electronegativity, right? How well it holds onto the electrons. These are usually saturated because they have a good balance of chi and r, so a radius that's large enough that can actually fit those, and chi that we can actually keep the electrons. Okay? So tends to lose the electrons, so you never get to the 18. Too small, can't fit 18 around. Yeah. And you can notice here, like for example, silver, if you looked up at the periodic table, we can see that it tends to be a little higher on the periodic table, and it also tends to be something that's very stable and bring in its electron pretty well. So let's try this. For each of the following organometallic molecules, determine the formal oxidation state for the metal. Let's count the total number of valence electrons the compound has, and justify why any unsaturated compounds have less than 18 valence electrons. Go ahead and just do the first two real quick, okay? So the N5 here, what does that mean? Yeah. So all 5 of those are bonded, aren't they? So it's centered on it. All right, folks. Let's go ahead and go on for this one. Okay. Next one, I'll go run and grab water. That'll really help. All right, so the first one here. So this is formally going to be a 6. What you see here is you have to total up your charges, of course. And so this one here is going to contribute 6 electrons. If we look at that periodic table up there, we'd have 6 left. And then what we're going to have is the N5 here is going to give us 6 electrons being contributed. The hydrogen here is 2 electrons because we got the bond there. This one's going to be another 2 electrons. And so that's going to only total up to 16 electrons. If we look at our previous table here, then we'd see that this is not predicted to give you 18 electrons, is it? It's too small. Okay.
Go back through how many electrons each one contributes. So the N5 would contribute
6.
5. Oh, it's 6?
Yeah, 6. One more. And then the hydrogens, these are just bonds, right?
Yeah.
Single bonds. So 2, 2. And then this one here, the 3 plus charge, you subtract 3 from the periodic table, and that needs to give you. If you look up the periodic table, it's going to have to give you 6. Okay.
And then just add up all the
So it'd normally be 9, right? Valence electrons. 3 plus charge, so it's 6 instead. And then we add up them. 6 plus 6, 12, 14, 16. Yes. You'd have to have a very, very unusual condition. Okay, so let's try the next one, TA. So this is going to be a 3 plus charge for the TA here. This is going to give us a 2. So the metal is going to give you 2 electrons then, because after we do a 3 plus, 3 electrons lost. TA is going to go down to 2. And then the hapticity for the CP here, these ones, that's 5 each. So we get 6 plus 6, 12. So 2 plus 12. And then we look over here, we have a single bond. And then this carbene is going to give us a 2 electrons because it only has the attachment here. And that's going to give us 18. By the way, even if you got confused here with these groups and looked at the double bond here, or the double thing and went in a double bond, you can't go above 18 anyways, so you'd have to go 16. Oh, I can't add another 4. Okay? So note that you can internally double check yourself on these things. Okay?
So if you didn't know the oxidation state, you're just adding a 12 from the N5. 14,
You
16.
do have to figure out the oxidation state.
Okay. And then how do you just...
So the oxidation states are going to be, do you remember where we did the previous chapter where we were talking about the d orbitals and the oxidation states? It's that. If you want, I can give you more information. Email me, but yeah. I can make a little video or something to go back over it. It's the hapticity plus 1. So it's this right here.
So, kind of going back to what you said, so even though
Yeah, so you can, this wouldn't be 20 electrons, it would be 18. This isn't meant to be a double bond to that. But even if you got confused on something, as long as you were only one group remaining, then you can always go, oh shit, that can't be another 4, because you can only get up to 18 in that valence shell. Yeah, you can't go above that unless you're down in the F block, and including the F electrons. Mm-hmm. Yeah, that's the valence electrons on this. So the D2 here is the electrons that are remaining on it. So that's the valence electrons on the metal that came from the metal. Mm-hmm. So 2+ charge here. Okay. And then we're going to have it having 4 electrons remaining after the 2+ charge on the valence electrons. And then we're going to go hapticity 5. So that's 6 electrons here, right? Hapticity 3. So that's 4 electrons here. Okay. And then a pair and a pair again. And part of what you can tell from this, there's another way to double check your understanding of this. For example, this one right here, this doesn't have any extra connections that can wrap back around. And so automatically that can only have 2 electrons on a direct connection, right? You would have to have another connection that wraps around. This would have to have a greater hapticity. Is that making sense? Okay, let's go ahead and go to the next item. If you guys want any more details on going back, please do email me and remind me, okay? Because I have some other stuff after this, and I may not remember by the time I get there. Okay, now this is going to be your 1 electron molecular orbital diagram for this. That's just your bonding molecular orbital diagram. So here we have our d orbitals for our chromium, and these are going to mix with our sp hybridized orbitals on our COs. Notice again, those sp hybridized orbitals are direct connection orbitals, right? Okay. And so this is what this is ultimately going to look like in terms of what we would see in these connections, okay? So this right here, if we're looking at the sigma donors, these are going to give you a rise in energy, and this is going to be on that direct overlap between one side. So for example, here we have carbon monoxide has a triple bond, right? And then they're going to have lone pairs on that. So if you're overlapping in the lone pairs, that's going to be a sigma overlap, right? Okay. Over here, we have more of a pi bond overlap, right? And that's going to happen on specific d orbitals only. They're going to have to be the d orbitals. Remember, your d orbitals had a variety of different looks, right, to them. One of those d orbital looks is the dxz's, right? dxy's, okay? That were in the plane. They look like clovers, right? Okay, these ones here. Okay, those can actually do a pi bond acceptor, or another way of saying it is they can actually look like pi bonds, right? Where we have indirect overlap. We actually saw that back in chapter 9, didn't we? Remember that back bonding? That's very similar to back bonding. Well, it is back bonding. It's just an application of that. Okay. And so this one, for example, right here is actually going to be good at accepting pi acceptors. And so if you have pi bonds that can accept, this is actually going to lower that energy and make that more stable. Okay, so let's talk about a little bit of terminology. This is actually one of the few things that you guys aren't going to be able to, you skipped in those chapters we skipped. So this is actually, as far as I remember, this might be only one of 2 things. So remember that your most commonly occurring type of complex for these is going to be an octahedral complex. Okay? And that's going to be where you have 6 ligands. They're going to form the vertices of an octahedron around your metal ion. So in the octahedral symmetry, your d orbitals are going to end up split into two energy differences because they're going to align well with that octahedral, or they're going to align in the horizontal plane of the octahedron, right? And there's going to be a difference between those. Okay? And so that energy difference is actually referred to as delta O. Okay? As in delta oct, as in octahedral. Right? And that's that energy difference between those d orbitals. Right? This is referred to as the crystal field splitting parameter, or if you're talking about ligand systems, it would be the ligand field splitting parameter in our case, or ligand field splitting also would work. Typically, though, you would put it as delta oct. You can also sometimes see it as 10 dq, and that's actually the number in unit it typically is 10 times the differential of quanta. So what's going to happen here is your dxy, dxz, and dyz orbitals are going to lower in energy. Your dz squared and your dx squared minus y squared, they're going to have higher energy. And that's because these ones here are going to be further from the ligands than these ones. And so those electrons that are in the metal ligand connection, coordination, are not going to interfere with these ones as much. They're going to cause these ones to become higher energy because these actually directly overlap those connections. They have some overlap, not completely, but is that making more sense? So these ones would be like think of it as like a sigma and pi bond, right? Okay. So the pi bond gets affected very little by the sigma bonds, right? Because it's above and below. These would be like that pi bond. They're above and below, and so they're not affected a lot. They're in the dead space between the coordinations, right? These ones, on the other hand, would almost directly overlap several of the coordinations. And so they become much higher energy because a lot of that space then has electrons that's right next to it, right? Repelling the electrons that normally go in there. Okay. So again, the three lower energy orbitals are collectively actually known as the T2G. The two higher energy orbitals are collectively known as the EG. You may have noticed that, and these right here, see that those were grouped together over here. The EG and T2G. Okay. Those are the irreducible symmetries of those orbitals. Yeah. So remember our symmetry IRRs on our tables of symmetry. Remember we're going to be an octahedral, right? And so these right there would be those symmetries. Okay. So again, those are the same ones from molecular symmetry that we did in chapter 6. They're the irreducible representations. Again, this would be the octahedral point group. That'd be your OH point group. There is one other one, which would be your tetrahedral complexes, which would be your second most likely. And this isn't going to be a huge thing that's going to come up a lot here, at least not from my memory. But you would have a directly analogous thing happening here, okay? Which would be that you'd have the tetrahedral crystal splitting field splitting, and the d orbitals would split into two groups again. That energy difference would actually be delta tetrahedral then, because it's the tetrahedral this time. And it would be these groups right here. The lower energy orbitals would actually be the dz squared, dx squared minus y squared. The higher energy would actually be the other ones. Yeah. And that's the dxy, dxz, and dyz. And it's the exact opposite of the octahedral case. It's because our tetrahedrals are now aligning with these orbitals, aren't they? Because we mixed an S and a PZ, an S and PX, right? S and PZ. And so now they start aligning with these orbitals instead, rather than these ones. And us having filled orbitals that are aligned with these orbitals means they're higher energy for any electrons that try to go into them, right? Is that making sense? Did I lose anybody there? Okay, so this is some structures of some of these ligand fields or complexes that we might see. So this is the structure of Mn2, and then we have 10 COs around here. And notice we actually have two metals here, the one acting as ligand to the other, don't we? Isn't that cool? Look at that. So that's a dimetal metal. So this is the structure right here of the cobalts, and what we can see here is we're actually going to share some of the COs and side overlaps. So your pi bonds are actually the ones that are responsible for bonding in this case, where it's sharing between. Okay? And that's why it's vertical like that between them. Okay? And then these are more direct overlap right here, sigma type overlaps. Okay, so this is what this sort of thing is going to look like. So here we have a sigma donation, and so this is going to be where your sigma donates into those orbitals and makes the connection with the coordinate right there. Okay? And this is going to be where we have a pi orbital making this donation. Can you see the sort of difference there? Yeah. And remember, these things happen, this coordination happens like this, because they're metals right here, right? And metals don't pull the electrons hard enough to actually move them out. Okay? And these are also d orbitals, right? And what do we know about d orbitals? They're pretty big, aren't they? They can get pulled out quite a far. Another way of thinking about that is they're very polarizable, right? Very deformable. Okay? And so they can make kind of interesting overlaps, like so. Do note that you still have more of a direct overlap in this case. And you still do have more of a side-to-side overlap, right? Okay. It's just not as nicely direct overlap as your old sigma bonding back in organic chemistry. Okay? Because you can have a direct overlap of two things here. Okay, so let's use some molecular orbital diagrams for CO and CN. Let's talk about why they have a cyanide ligand will often form ambidentate. That's two metals attaching to it. Ambi both sides, right? Dentate, as in dental, because ligand is like a jaw snapping closed, right? Okay. So this is ambidentate. Bridges. But why the carbonyl ligand bridging in this fashion is quite rare, actually. Okay. So I'm going to let you think for a bit, and I'm going to go on fairly rapidly, because I'm not sure how much you can actually get forward. I don't know how much reading you did before this either. Okay. So the big difference here is electronegativities, right? So when we have the carbon-oxygen versus carbon-nitrogens, your biggest difference is going to be the electronegativity difference between oxygen-carbon and carbon and nitrogen, right? They're going to be very similar structures for these in terms of numbers of electrons, right? They're going to have the same number of electrons. Orbitals are going to fill pretty similarly. But your exact energy level for these different orbitals is going to change. And that's because in the oxygen, these electrons here, these orbitals, are going to be lower energy, right? And so they're going to be pulled down. Nitrogen is going to be closer to carbon in energy because it's less electronegative, right? Or another way of saying it is the lowest energy orbitals are going to share more character with our oxygen. The higher energy orbitals will share more character with the nitrogen. Okay, and so we then fill in these electrons. So again, we have the s orbitals giving you these ones down here, which don't really do much for us. And then what we have up here is we have these ones giving us the lower energy pi, the higher energy sigma, and that's our HOMO, isn't it? And then up here we have the pi anti-bonding, and then sigma anti-bonding. And so in the case of oxygen to carbon, these upper energy orbitals here, these LUMOs, they're going to be more carbon character, aren't they? In the case of nitrogen, they're going to share more of the nitrogen character than they did over here. Okay? It's the orbital mixing. Yeah, it's literally just what orbitals, atomic orbitals, are closest.
Oh.
Yeah. So in the case of this, where you have something very different electronegativity-wise, the high energy ones will have more of the less electronegative one. The more electronegative one will always be the closer to the lower energy orbitals that were mixed to make it. Yeah. The lesser you have of the difference here, the more even the mixing will be for all of them. Okay? This will still have more carbon than nitrogen up here, just not anywhere near as much as the oxygen would. Is that making some sense? Okay. So this right here is going to be your HOMO-LUMO set. Again, your LUMO set right here is going to have it where it has a pi character, right? And so we'll have a pi bond type character. And over here we have a sigma type character. And this is our HOMO right there, right? Okay. Everybody okay with that? Okay. Now, remember, these are going to be larger oxygen characters for these higher energy ones, right? In the case of nitrogen, these are going to be much more even, aren't they? And so we're going to have more nitrogen character in these. Is that making sense? Okay. Okay. And so when we look at this Cn here, right? Which of these is going to have those electrons that can then bind onto these ligands? Well, this one, the carbon, right? This one, they're actually pretty even compared to the carbon and oxygen. So you can actually do either. And so this one's going to be much easier to do bidentate with, right? Because you can do either one fairly easily. On the other hand, the oxygen here is going to be very, very difficult to pull electrons from. It doesn't have the higher energy electrons to work with, right? It has the low energy ones. Okay? Did anybody get confused and get lost? Okay. Sometimes I can't tell from you guys' faces. Like sometimes you obviously look confused, but sometimes you just look sleepy. I don't know. All right, so this is your binary organometallic compound. It's going to contain an ambidentate bridging carbonyl ligand here. And it's actually pretty wild looking, isn't it? Yeah. So again, binary organometallic. Everybody's comfortable with that language, right? Binary because two metals, right? Organometallic because metal and organic right there, of course. And ambidentate because it's binding to each side of this ligand, right? So ambi, both sides, like your hands. Okay. Okay. Note that almost all of the language in here is actually like hand, claw, biting based. So it's all like that. Okay. So if you think you know what it means, you probably do.
The example of the molecular orbitals, was that saying that the nitrogen is more likely to form the...
Yeah, then the oxygen would.
Okay, but, and then this is just showing it still can't. I guess.
Yes, it can.
Okay.
Yeah.
It's just not as...
Yeah. It's just not as prevalent as the other one. You have to have something a bit more charged over here, or yeah. Yeah. So this one's just more common. Yeah. Of course, your book uses some really wild examples because like these are actual real world examples, and this guy's very knowledgeable about the field. So okay. So anyways, partially what I'm doing in these things, I'm going to show you reactions. I'm going to show you structures because you need to get comfortable looking at these things, right? And you need to get a buildup of like examples that you can reference back in your head, right? So for example, if you ever look at something that looks like this and you see two metals attached across, what is that called again? Yeah, binary organometallic compound or complex. Compound would be a nicer way to do it, but no, complex.
The thing is just when it's like a CO or
Yeah.
CN.
Yeah, when the ligand is attached on both sides. Yeah. Pretty common in these cases. I can't think of any examples that don't have ambidentate ligands, but I want to say you couldn't come up with something. I have not exhaustively looked for that ever. So your metal carbonyls, these are some different ways that you can synthesize these. You can direct reaction with a zero valent metal with CO and gas at elevated temperatures. Usually you have to be pretty hot. And so this would actually give you your direct reaction right there. And in this case, we have iron, just metal, and we're reacting with CO, carbon monoxide. Okay. We could do the reduction of a metal precursor in the presence of CO, carbon monoxide again, gaseous form. And so here we already have something that's fairly, CH3 attached to it. We have these methyls attached to it. And then what we're going to do is we're going to have it in the presence of carbon monoxide gas. We need extra of those than just what replaces the metal because we're going to end up doing a reduction here of that where we're going to react the CH3s with this. And so we'd actually react the CH3s and then we'll replace those as we go along. This is going to be your ligand substitution with carbon monoxide. And so right here we have some ligands. They don't necessarily bind as well as carbon monoxide. You can somewhat counter this with the proper pressure and temperature considerations. Like if you have enough CO at high enough pressure and temperature, you can drive this reaction. Okay. Though at some point you're not going to be able to replace ligand. It binds well. Right. This would actually produce water here because one of these is water, right? And we'll replace that water with carbon monoxide instead. This is going to be deinsertion. So right here we actually have a methyl with a carbon oxygen on it, like a carbonyl group, aldehyde, that sort of thing. And what we have here is a chloride. And what we're going to get is the reaction with this to remove the oxygen. We'll remove one of the PPHs right here. Does anybody recognize those, by the way? So this right here is very analogous to the Wittig reagent back in organic chemistry. You know, right? So this is a phosphorus with 3 phenyl groups around it. And so that's that thing that you, to make the Wittig reagent, you'd use one of these, and it would bond to a carbon, and that would make it negatively charged. Okay? And actually, you're doing something very, very, very similar here. It's just you're starting off the metal here that's attached to it, and then you're going to overlap those carbonyls. You'll make a 4-membered ring, and then you'll swap them, just like you would have for a Wittig reagent reaction. So it's actually almost the same thing. We just have a metal involved this time. Yeah, pretty wild, right? Everything connects, doesn't it? Oh my goodness. Okay, so these are going to be nitrosyl ligands. So this is going to be a very, very good sigma donor. It will actually be a good pi acceptor as well. They're not necessarily a good pi donor. Okay. It can serve as either a terminal ligand or a bridging ligand, which we actually see examples of in here. For example, right here, this is terminal, right? Terminal. This is bridging, isn't it? Where it's bridging across. Mm-hmm. Yes. Yes. Those are just different structuring of it. Or another way of thinking about that, those are the canonical structures. So if you have something, so think about it this way. You'd have canonical structures for the NO minus, right? One would be a triple bond. One would be a double bond with lone pairs. If you have something that can stabilize those lone pairs, then this is going to become a more prevalent canonical structure, right? And that's what we're seeing here. We have this fairly charged metal that's going to be able to stabilize that lone pair. Okay. And so that's what you're seeing. And you're seeing another example here where we have two of the chromiums stacked together to stabilize those electrons. Okay. So you have two modes of bonding, which we're seeing here. We have one where the ligand has a +1 charge. It's going to have the NO triple bond. It's going to be sp hybridized. And so it's going to tend to form a linear structure where your metal and then nitrosyl is mostly linear-ish. Okay? Like 165 to 180. Does everybody understand why you only ever go up to 180? Because if you go the other side of 180, you're just going backwards in this, right? Yeah. Okay. So that's actually this example right here, where you can see it very clearly drawn, so it's very linear, right? Okay. So again, you have a triple bond. So that NO triple bond is going to have frequencies at very high wave numbers, just like you would have expected from the infrared information that you saw back in organic chemistry. And so you're going to typically see those bands somewhere in the 1610 to 1830 wave number region, like you would for a lot of the NO triple bonds, or if you looked at like a CN triple bond sort of things, that sort of stuff. Okay. Very similar region, a little different because you're typically bonding to metals. So you can get some electron withdrawing effect, right? Okay. So the NO has a NO double bond canonical structure as well, and that NO double bond is actually going to be sp2 hybridized. And notice here, we need the sp2 hybridized orbitals to overlap, don't we? That's like a trigonal planar structure, isn't it? Yeah. And so that's going to be the NO double bond one. And so it's going to bind to a metal with a bent configuration. That's the bent configuration, right? If we don't look at the oxygen. Yeah. If we look at the oxygen, that'd be trigonal planar, right? That's going to be about 119 to 140. These things are going to be very, very variable because they only have to overlap with d orbitals on metals that are fairly large. And so you're talking about extremely polarizable orbitals, right? That can bend a lot. And so we can actually get a lot of deformation to give us the least amount of steric hindrance possible. Okay. So this is one of the ways that like the organic stuff is still kind of true, but we have a lot more wiggle room in this, don't we? Okay. This is that right there. And this one right here also, because it has an overlap like this, where it's on the top there, it's going to be better overlapped with the sp2 overlap. Less steric hindrance. All right. These are going to be NO double bonds, by the way. And so they're going to absorb in about the NO double bond region for the infrared. And so that's going to be 1520 to 1720. Do keep in mind they have a fair range on these things, again, because they're typically going to be bonded to metals, right? And so you have a lot of electron withdrawing and promotion effects you can have. Yeah, they have some interesting behaviors in themselves. So for the bridging carbonyls, by the way, if you have a bridging NO, that stretching frequency is going to be lower in energy than the terminal counterpart. So if it's terminal, it's going to be higher frequency. bridging, lower frequency. So it's one of the ways you can give evidence for it being a bridging structure. Okay. And so what you typically see is you'd see frequencies there in the 1683 to 1625. This would be your C here, where it's bridging. And so that's going to have a bridging stretch frequency at 1499. And so that shifted downwards. Okay, and so this right here is your sigma overlap. This one right here is a sigma overlap to the side here. And so this is going to be with the SP linear, where you're going to have a very linear overlap that's in line with that triple bond, right? Okay, and that's going to give you the 180-ish. Okay. Note that the formal charge here is going to be +1 on the oxygen, right? Because that's one of the possible canonical structures. This being, I don't know if you guys ever drew out NO. Have you guys ever drawn out NO for the and done formal structure, formal charges for NO or NO2? Okay, I don't remember if I did that to you. So this is actually one of the ones they should. I've never seen a general chemistry not give it. I always give it, and everybody I've seen gives it. Because it has interesting behaviors like odd numbers of electrons, radicals, formal charges on oxygen if you do one of the canonical structures. So it's kind of the one that sort of like makes people buck their heads out of these very strict, rigid idea of what these things can do. Okay? And what you see here is if you do the triple bond, because oxygen has an extra valence electron, right? Normally it's donating that extra electron in, isn't it? And so it ends up with a +1 formal charge. And so canonical structure-wise, this is a good canonical structure, but it's not as preferred as you might think. Okay? In fact, it's some cases not preferred, as we were just seeing, didn't we? And so over here, this is the sp2 bent one, and this one has a formal charge of 0 on the oxygen, where it has a formal charge of 1, -1 on the nitrogen. And so again, it has the wrong charge on the wrong one, doesn't it? So you always end up with the wrong charge on the wrong one for NO, nitroxide. By the way, this is one of the reasons why like your cars work, by the way. Yeah, your catalytic converter. It's one of the reasons why that works. Because NO is one of the things you can produce, and if you put it out, it would immediately react in the atmosphere to NO2, and that gives smog. So they use the residual heat to keep your reaction going, and then a catalyst, and it ends up being thermodynamically unstable to be in this form. And so it converts back to nitrogen and oxygen. This only gets formed in cars because it's so high energy. So yeah. They're typically not as stable unless you stabilize them with something. Say maybe a metal. Anyways, did that make some sense? Fantastic. Okay, so let's try that out. We have here RuCl, NO, and then there's 2 of those, PPH3, and there's 2 of those. And that's a +1 complex. It's going to exhibit 2 stretches in the vibrational spectrum, one at 1845, the other at 1687. So let's sketch a reasonable geometry for this compound. I'm going to let you work on that for a bit. I'm going to go grab water real quick. Okay? How am I doing for timing, by the way? Oh, never mind. So much for that. Okay. I will do this problem. I guess we'll call that almost a day. Yeah. So what do these frequencies tell you right here? If you go to that previous slide. Yeah. It tells you which of these it is, isn't it? Okay. We don't have to worry about bridging in this case. It's not an issue. And so one's bent, one's linear, right? Those are those, right? One was in this, one was in that one, wasn't it? So yeah. Okay. Okay. Note, by the way, if you have a difference between bent and linear, even if they're in that part where they kind of overlap, 1720 to 1610, if you have two peaks that are different, it's very likely if those are just a mono metal, if you just have one metal here, not binary, that you would have the same sort of bonding around, right? You'd have very little differences if you're looking at the same things. Okay? So it having a pretty big difference between these right there just tells you it has to be the two forms. Okay? If it was the same thing and it's just different geometries, they'd be very small differences. Okay? But you could still get like an 1845, 1830, that sort of thing. Yeah. Okay. So again, we have linear, we have bent, and so we're going to surround this with these groups. We have these 5 groups right here. And so this one's linear, so it's going to surround in a position where linear would be at advantage, right? Which is that sort of 4-membered square at the bottom, right? And then this one's going to end up at the top, where it being bent is not going to be an issue. Or actually a strength, depending on the size of these groups, right? Okay. Okay, everybody's comfortable with the P is the P, pH. Nobody has a problem. Okay. Okay. These are the reactions here. So we have the nitrosyl compounds again. They're going to have the direct substitution of the NO for the CO ligand here. And so we have the CO ligand that's already substituted. We put that with NO gas. That's going to then have a direct substitution of the NO. So this is going to be substitution of the CO with NOCl, or we could use NO plus, or we can use NO2 minus. The negatively charged NO2, nitrogen dioxide. So this is going to be the NOCl right here. We put that in with, and what you're going to see is the chloride is actually going to take the electrons, and then the NO is going to come on here to use up some of that electron density because we had a negative charge before. Over here, we're going to have this complex right here, and we're going to have the NO plus. This is actually just going to insert, because it's positively charged, we're going to end up with a positive charge overall. And so what we're essentially have is we have a buildup of electron density, which we're just inserting and taking because we're positively charged now. And we're much more electronegative than the metal and most of the other species in here. Okay? This one right here is going to have your NO2 minus. So the NO2, then a minus. I have to be careful there. And in this case right here, what we're going to see is the COs here. We're going to react with CO2 and water. This is actually going to make carbamic acid, the same sort of acid that you see in your blood, which is quite stable, by the way. And then we're going to insert NOs in here. Okay. Mm-hmm.
Going back to your example, I just want to be sure I'm accurate.
Mm-hmm.
You said that you know that two separate ones just because they're nowhere near each other.
Mm-hmm.
The wavelength. So, like you said, it was like 18 or 18,
Exactly. Yeah, if you had something that was really close, notice these differences are something in the order of like 200-ish, right?
Mm-hmm.
Yeah, 150, somewhere in there. So if you're up in the 150, 200 range, it's the different types, right?
Mm-hmm.
Even if it ended up falling into 1700 or something, which this one actually falls into that range. It could have been either, right?
Yeah.
Yeah. But this one tells us very clearly, yeah, if it was the other linear one, right,
Mm-hmm.
it would have to be somewhere up near this one. Because the differences that we're seeing here are because of the metals. So, for example, if you had something that was very high charge, like a 5 plus, 6 plus, it would shift it considerably versus a no charge Fe0, right? Yeah, that'd be a huge shift in these frequencies. Yeah. But we don't have to worry about this in that case because we just have the one metal, same metal for both. Does that make any sense?
Yeah, I was just.
Yeah, I always have to wrap back around and make sure I made sense because sometimes I do not. I cannot find any time that would work for you guys and me. What time works for you guys? Like, nobody wanted to do it the week before. I can try. One of the weekends I have things I need to get done. Okay, so let's try to set a schedule time right now. Let's see. I cannot do it the 18th to the 20th, the Easter weekend. I don't think anybody would have been there anyways. So, I could do any time. Well, I can do any night or on the weekend of 21st to the 27th. Oh, by the way, the two new people, none of the time slots that we had work. Yeah. Sorry. No, really sorry. If you guys can end up working out of the time slots and stuff, we can try recommunicating that. But I have a funny feeling I'm actually think I get another like people maybe. And yeah. But so does 26, 27 work for anybody? Or one of the nights of well, let's see, that's except for 24th. Huh? Yeah. That's gonna be the ACS exams that Friday, but yeah, we could do that Friday night or something. Yeah, that's no problem. It's like next week is Good Friday, right? And so like the weekend is not gonna be an option.
But is that weekend a 4-day weekend for? Do we get Friday and then?
I think it was Friday.
Friday.
And you get this.
Try the
Next month.
next Wednesday evening
Yeah.
after.
Next
Let me try to schedule it. See if
try to schedule it like here.
Yeah, you guys are tough to schedule, I'll tell you that. Oh, it is. Yeah, you're all doing things like y'all have activities, work, and then we all have slightly different schedules. So it's been a
No. Yeah. No, just finish.
You definitely should, Jim. Terrible idea. Okay, everybody was good for ACS being on Friday. What was the decision for the ACS? Friday.
I was looking at that schedule like we have an exam every single.
Yeah, I thought it might be better just to
Also,
Double up.
lab tomorrow.
Mhm.
There's since me, Aiden, and Joe, you said groups of two, but there's an odd number of people in the class and
That's fine.
us three.
Yeah, that's fine.
All right, thank you.
Definitely.
Oh, and also, can we show?
Positively or negatively there?
Just very dense.
That's
Um,
fair. Okay, where'd you get?
It was what was it?
16. Yeah, it was when it worked for people during the evening, but I'm during the afternoon / evening. But I still need to check if it works for them.
Like after 2, probably then.
Yeah, that sounds like I think that would probably work.
Then yeah, as long as it's just after, because I just have a
After 2 p.m.?
class. Yeah, that would work for me.
Sounds good. Your class ends at 2 p.m.?
It's like 1:45 or
Okay.
yeah, 12:30, 1:45. But I like to round up just in case, whatever reason.
Contact them some back. Never did it.
This semester is quickly coming to an end. Crazy.
Yeah, it is. Wrapping up.
Yeah.
I need to somehow figure out how to get all my graded. Figure out how you're gonna go to A4 and take it.
Yeah. you still need to grade the organic.
Yeah.
Or at least submit. I just want to see the zip grade like my raw.
Oh, it should be available.
I didn't see it.
Sure.
I might be putting in the wrong. Yeah, no, there's no way this is brain organic. I got 70 on this thing. I got like a 20% organic chemistry.
Okay. So can you see the organic exam one?
I just see exam one still.
Oh, okay.
I've been checking it like at least 3 times a day.
Yeah, I've been God, I've had a lot of trouble getting the people at Mist and organic chemistry to. Oh, wow. That has been brutally difficult to get to work. Tell you what, students are like. You know, have you ever heard of rounding up cats?
I have not.
It's like that. um,
Ending up.
you know, you get a group of cats and you try to get them all in one place.
I don't have cats, but I think I've
Never seen anything like it.
There's like a bunch of stray cats right around my house.
They never go in the same direction, right?
No,
At all.
they're all around.
Yeah, that's what it's been like this semester. I tell you. Oof. Nobody like even this, right? When do we have the time that's the same?
Yeah.
I'm not available this time. I'm not available. This time. Nobody has time the same. Okay. Ah, man. We got everybody. Okay. It's released now.
Cool.
And the score sheets are released. The proper answers. The whole test is released, so you guys can see it. So you can use the stuff. Now, keep in mind there is a curve, and there's also the I need to grade the other section.
Oh yeah, so this is just counting.
Yeah, that's an absolute.